Well, thanks to everyone for tuning in to our webinar series on fire retardancy. My name is Haskell Beckham, and I'll be serving as your moderator and host today. Before I introduce today's speakers, I'd like to tell you a little about the webinar series. This webinar series evolved from member requests to the staff at the Industrial Fabrics Association International, as did the topical outline shown here on the left. The plan is to cover the topics in a series of webinars held approximately every 2 months. The topical outline and the schedule will continue to evolve based on member and participant feedback and requests. So please keep the feedback and comments coming as we move through the series. We started this last fall, so we've actually been through a number of those topics. Today we are pleased to present our 4th webinar in the series with an overview of testing textiles for flame retardancy. On April 19th, Calvin Shen will deliver a webinar on commercial flame retardants, properties, and applications. Future dates and specific topics are to be determined, but as I mentioned, the tentative plan right now is to schedule a webinar about every 2 months until we get through all of the topics shown there on the left. So let me introduce our speakers today. We have 2 speakers today. It's going to be a tag team effort. Dr. Alex Morgan is a distinguished research scientist and the group leader for the Applied Combustion and Energy Group at the University of Dayton Research Institute. Dr. Morgan has over 20 years of experience in the areas of materials flammability and retardancy, fire science, fire testing, and fire safety engineering, with an emphasis on chemical structure, property relationships, and fire-safe material design. He's helped academic, government, and industrial customers solve their flame retardant and fire safety needs in a wide range of applications. Prior to joining the University of Dayton, Dr. Morgan spent time at the Dow Chemical Company, where he initiated a new program in fire safety for plastics, and at the National Institute of Standards and Technology, otherwise known as NIST, in the Building and Fire Research Laboratory. Dr. Morgan is on the editorial review boards for Fire and Materials, and is the editor-in-chief for the Journal of Fire Science. Our second speaker today is Andy Blum. Andrew is a managing engineer at Exponent. He is a registered professional engineer and certified fire and explosion investigator with over 10 years of experience with fire testing and investigating losses due to fire. He has specific experience with textiles and clothing, including firefighter PPE and upholstery, as well as many types of building materials and consumer products. He has conducted both small and large-scale fire testing according to nationally and internationally accepted standards, and is a principal member of committees that serve numerous organizations focused on fire safety, such as the International Code Council, ASTM International, and the National Fire Protection Agency, or NFPA. You'll hear from Andy after Alex gets us started. Please note that if you have a question during the webinar, please enter it on the GoToWebinar toolbar. We will address the questions at the end of the presentation. And so now I'm going to turn it over to you, Alex.
Okay. All right. Can everyone hear me? I'll take that as a yes. All right, so my name is Alex Morgan. I'm going to talk today, the first half of the talk. I want to thank Jonathan and Haskell again for inviting me, and as well as Amari for the web support. This is the outline of the talk that I'm going to give today for the first half, talking about fabric flammability and risk scenarios, because when it comes to flame retardancy and fire safety of materials, you try to design to a particular risk scenario. You can't design for a universal fire test, so you have to look at each of the risk scenarios. So I want to talk about that a little bit. I'll talk about some heat release-based fabric flammability testing, the relationship between heat release and fire performance, and then we'll switch over to Andrew, who will talk about regulatory and industry fire tests, and then he'll lead out with conclusions and summary. A little quick background on myself. So, again, Haskell, thank you for the kind introduction. So people have maybe not heard about the University of Dayton or the Research Institute. We're a federally funded, or we are federally funded, but we're a contract research organization with the University of Dayton. We do a lot of federal research, but we do work for other people as well. We're number 2 in the United States for federally funded material science. We provide a wide range of research, development, testing, and services. So a lot of what I'm presenting today is based upon the type of things I do for my customers. Customer owns all the intellectual property, so if you're interested in, if you see something here today you think I can help you with, please let me know, and again, offer a variety of services. All right, enough advertising. So fabric flammability and risk scenarios. When we look at testing of materials, for those of you who on the phone may be required to have a textile formulated to meet a particular test, you're probably wondering why. And this usually goes back to some historical event that caused somebody to realize there was a fire issue with textiles. Textiles and flammability have been around for a very long time. Some of the earliest recorded examples of fire protection are on wood and natural materials, but the beginnings of flame retardant chemicals for textiles began in the early 18th centuries with the French scientist Guy Lussac, and that was based upon candles igniting opera curtains in Paris. So it's always a reaction type based fire need. And so at some point somebody realized there was a fire hazard, the potential for property damage, injury, or other type of loss due to the presence of a fire. And that can be kind of a broad definition, as you can see from what I've written here, which is pretty much pulled directly from the Society for Fire Protection Engineers SFPE handbook. The hazard can be small, it can be a localized burn injury, or great, entire loss of structure, loss of life. So once somebody's identified a hazard, then they start looking at what's the risk, what's that potential for loss as a function of that fire hazard. What are the chances that fire could occur? Maybe there's a chance that the building could burn down if that fabric on the wall catches fire, but maybe the chance of it burning down the whole building is only 1 in a million, so they look at it as a different fire risk, and therefore there's not necessarily a fire hazard that they need to worry about, even though that hazard may be there. And then that all gets rolled into the fire risk scenario, specific situation and environment where the fire hazard can occur with notable or known fire risk. This is where, again, it's done in a reactionary mode. Once the fire risk scenario is identified, then people start designing the test to address the fire risk scenario. And that's what we're going to kind of focus on today, is we're not going to address where these fire risk scenarios historically kind of came from, but instead kind of walk you through why these particular things, how you test for them, and then talk a little bit about some of the chemistry and some of the other things as we go today. So once you have a fire risk scenario, it's up to a fire safety engineer to kind of assess that and then figure out how they're going to address it, whether they're going to, this is a simple scenario or whether it's a more complex scenario, and then what type of fire protection they need to put in place. And then that will kind of govern the test, as well as what solution they may choose to use for that fire protection. Do they use a flame retardant chemical? Do they use an inherently flame retardant fabric? Or do they just use an engineering scenario where they get the fabric away from the fire? So here are some specific fire risk scenarios that I pulled up that are relevant to those of you on the phone today. They're highly varied. So you've got your ones currently in use today for upholstered chairs, cigarette smolder leading to ignition, and this of course is probably could be another half-hour talk in itself about all the controversy between open flame and cigarette ignition and what actually happens for upholstered furniture and what all the data has to say. But that's one scenario. Guy falls asleep or a cigarette rolls into the couch cushions, into the corner, then that smolder, and then that transitions from smolder to flaming, leading to fire loss. In FPA 701, the small flame, candle, landing on curtains and the flame propagating upward. Post-aircraft crash fuel pool fire type tests. So that's another extreme of fire performance for fabrics. The seats that we all sit on aircraft have to meet some very rigorous fire standards, and that's this FAA oil burner test where they'll make a whole mock-up of the chair and literally set it on fire, but the fabric and the foam and the entire chair have to perform. So this is a composite test. While fabric's only part of it, it is relevant to the fire scenario. If the fabric kind of burns up too easily, the whole thing may not pass. And then there's these interesting EU rail and subway tests where they test the seat and the fabric on that seat for fire protection, and then they deliberately vandalize it. They cut it with a box cutter and then ignite it again to see if you break that protective outer barrier, what happens to the overall seat and assembly inside that train car or subway car, and then how does that propagate and lead to fire loss, or does it? So these tests always attempt to mimic the fire risk scenarios, but they don't do it perfectly. Testing is designed to be something that's reproducible, that everyone can do it, but fire is highly varied. It can be very chaotic, so it's not always perfect. It may not capture every nuance of a fire risk scenario perfectly, especially as technology changes over time. So most of these regulatory tests are pass-fail, but I'm going to talk a little bit about heat release testing because that's a little bit different. It quantifies flammability via heat release, and that can give some insights into how fabrics contribute to fire and can give you some data above and beyond just a pass-fail result. So one example of heat release testing, not commonly used for fabrics, but it can be, is the cone calorimeter, which you see here on the screen. This is an ASTM standard, E1354. It's also an ISO standard 5660. This test measures the inherent heat release of a material via oxygen consumption calorimetry, and you can read all this on screen as well as I can. Bottom line is where this can become very useful is if you're comparing different fabrics together, you can quantify that particular heat release. Okay, I burned this type of fabric, how much heat release does it give off? I burn this one, how much heat release does it give off? Assuming the fabrics are roughly the same density, you can actually compare apples to apples at that point and say which ones are higher heat release. I'll give some examples of that here in a minute. But the other advantage of this is that within the standard is there's modifications of the standard where you can test composite assemblies. You could put a fabric that's maybe going to go on a wallboard or some sort of structural, and you can back that fabric with that whatever it's going to be mounted on and test that entire assembly and see how it's going to perform. You can also do the same thing with fabric and foam. You can make little miniature seat cushions, put them in here, and measure that entire heat release and give yourself some idea of how is my fabric performing in combination with other materials. And the heat release can then quantify that and give you a lot of other data too, smoke data, carbon monoxide, carbon dioxide release, and so on. And bottom line, and so on this next slide, you see some pictures of the cone calorimeter, just the cone calorimeter to the left, and then this is on a close-up shot of the sample that we're testing over to the right. These particular assemblies and everything else, you kind of need to know what you're doing, but then they give you these inherent heat release. The higher the heat release, the more flammable it is, and it's kind of obvious. But relevant to fire risk scenarios, the higher the heat release, the more likely the flame's going to spread, or the more likely that that object may in turn ignite something else nearby simply by radiant heat. So going to this slide where we're talking about fabric heat release testing, you can look at a variety of different measurements from the cone calorimeter. And again, they have been correlated to some things, such as single burning item and wire and cable burn tests. For fabrics, again, like I kind of said, you don't test a fabric by itself in the cone, although as I'm about to show you, you can, and you can get that particular data, but then you have to kind of realize that that's just the snapshot for that particular fabric. It's that fabric in combination with something else is really what you may want to test on the cone calorimeter to properly see that composite performance and understand peak heat release rate. How fast does it get to peak heat release rate? Is it really, really slow? The fire takes time to build up, or does it instantaneously ignite, go rapidly to peak heat release rate, and then suddenly burn itself out, indicating you'd have a very quick flash of fire once the material ignited. You can also look at some of these composite measurements like fire growth rate or FIGRA, where you take the peak heat release rate and divide it by the time to peak. So here's some examples of fabrics that I've personally tested or data that I can share. So we were actually looking at a test for the United States Army. They were curious how their fabrics were holding up as a function of getting washed, because you can imagine the soldiers wearing this uniform day in, day out. They get dirty, they need to be washed. Well, is the flammability durable with this flame retardant Army combat uniform, FRACU? And so they washed it once, they washed it 15 times, and they hit it with a very high heat flux to try to mimic blast conditions, since the heat flux of 85 kilowatts, and they see no notable difference. So here's an example of where just the fabric itself, you can get some useful data. Here's another example where I mentioned foam and fabric assemblies. So here on the left, we have a, if I remember correctly, this is a cotton polyester Bermuda fabric with a polyurethane foam. We made one of these little cushions I was describing. There's no flame retardant in it. So you see the heat release on the left, and then when you put the flame retardant in the foam, you see that the heat release begins to decrease over on the right, indicating the flame retardant's having an effect, and then the fabric's just kind of along for the ride in this particular case. But if you test the individual components, you'd see a much different picture. You'd see something, if you just tested just the fabric, you'd probably see something more like this slide with a single peak, and then the foam would have its individual peaks. But when you test the two together, you get a little bit better insight. And again, you're going to quantify some of the heat release performance and how flammable it is. There's another technique that you can use for fabrics called the microcombustion calorimeter. This is ASTM D7309. This is a fairly new test relevant to most fire standards. This test has been around since, if I remember correctly, 2007 was when it was first released. They just have a new version of it now, -12, that was updated in 2012. It measures milligrams of material. So this is a nice way to look at the inherent flammability of each fabric by itself. So if your fabric's nice and uniform, even if it's, let's say, a blend of two different fibers, it should be uniform at the milligram scale, so you could quantify heat release of this polyester to that polyester, this cotton to that cotton, this cotton to that nylon, or whatever blend, and then you can quantify that heat release. And there are some correlations to some other techniques that are out there. And Underwriters Laboratories is suggesting using this technique as quality control for certification of flame retardant materials, predominantly plastics. They're not talking about using this for fabrics, but if the correlation can be established, you'd find that this is a very simple, easy test to run, and then you could use it for quality control on your materials to confirm they're consistent from batch to batch, or as a function of how the fabrics are woven together, printed, what have you. This is a little bit how the test works. So a burning polymer goes from solid to gas to flame. What's interesting that a lot of people don't realize is that once a sample ignites, post-ignition, pre-ignition, it's all aerobic decomposition. It's the materials decomposing, mixing with air. Once the sample ignites, however, all the oxygen is consumed in the flame front, and then under the flame front is just pyrolysis. It's actually anaerobic decomposition. So post-decomposition, there's no oxygen that your sample is seeing, and so it's all pyrolysis. And so you can mimic that with the microcombustion calorimeter. The sample gets inserted into a pyrolyzer zone. It's heated up at very fast heating rates, 1 degree Celsius per second. That's all under nitrogen. The gases are then pushed into a combustor where they're combusted to completion, and then you run it past an oxygen analyzer, and just, again, oxygen consumption calorimetry equals heat release, and you get data. And so here's some examples, again, looking at that same thing where I was talking about in the previous slide, where we're looking at the functions of fabric washing. So we took a little microscale effect at it. It's okay, in the cone calorimeter, we're not seeing any differences in heat release, but what about when we take the fabrics and we wash them? Do we see any difference in the microcombustion calorimeter? And the answer is yes, we do. There's some minor tweaks, as a function of the washing. There's some minor reductions in peak, which is some of the initial flame retardant washing off, and then after that, there's no change. So after the first wash, which is data I'm not showing here, you see a slight reduction, and then it stabilizes. So the stuff on the surface of the fabric washes off, but then what's embedded in the fibers is still intact. And then you can get some additional data about rates of decomposition for the different fabrics. There's actually 4 different fibers inside this uniform, and you can pick them out. There's the first one, the second one, the third one, and the fourth one. And this data is published in this particular paper down here. You can also use the microcombustion calorimeter to look at individual fibers. And so this is a project that we just finished where we looked at a bunch of natural fibers, and they were supposedly all natural fibers, taken from plants, all undyed, but they're all different. So bamboo, cotton, flax, hemp, jute, kapok, ramie, and sisal, all different types of natural plant fibers have very different heat release profiles. Even cotton, depending upon how it's been chemically treated. So the raw cotton from the seed pod has this level of flammability. If you remove just those base oils, the flammability goes down, so it's actually even less flammable after you retreat it from the raw seed pod. But if you bleach it and scour it for medical grade, then the flammability goes up. And that can be explained by some of the chemical functions of that fiber. So This technique can be very useful for screening through different types of fiber sources prior to weaving them into a fabric and then considering them for a flammability application. There's also the OSU calorimeter, which is a heat release calorimeter, but measures heat release in a little bit different way. It is used for some maritime and mass transport applications, which is why I wanted to comment on it. It's not a test on fabric alone, but it's always a test on the assembly inside an aircraft or inside a ship or inside something else or on carpet pieces, but it's the carpet on top of something else that you're testing. So it's important to kind of, this is a good example of an assembly test, but it's a heat release test. And so it's a radiant panel that radiates heat onto the sample, and then you ignite it with a pilot flame, and then the heat release, that the materials decompose, and you measure the heat release with a thermocouple measurement. This is a picture of what it is and what it looks like. So your sample kind of sits right in here, and then it's in a vertical orientation. So the sample can drip and flow down into the apparatus, but the flames then kind of go up, and they're measured up in here for heat release. So in the OSU calorimeter, you're testing that assembly. So really you're seeing, the heat effects of the entire system together. And so you can't be, again, as I say here, heat release should not be expected to be the sum of the materials combined. You can see antagonistic or synergistic effects of that substrate and the fabric on heat release. And then the heat release in the OSU is measured in a little bit different ways. You can't correlate cone and OSU. But if you have to do this particular test, it's a nice way of sort of saying, okay, when I put my fabric and other component assembly into a vertical orientation mode, and it's going to be inside an aircraft or something else, here's how it's going to behave, and you can get some insight on the behavior above and beyond just a pass-fail result. Although the OSU calorimeter does indeed have pass-fail criteria based upon the numbers, it's still somewhat useful to look at the actual data you get, that heat release is a function of time, and give yourself some insight into the fire behavior. Bottom line is heat release, will affect fire growth rates. The higher the heat release, the faster that heat transferred to nearby fabric or other flammable materials. The faster the heat transfer, the faster the fire growth rate or spread across a particular fabric. But there's also textile fire physics and chemistry, which are going to affect your fire growth rates. Does the fabric char? Does it melt back? Does it curl away? Does it fall apart? And that's all going to affect your rate of flame spread. I mean, it's not uncommon for thermoplastic fabrics to melt back, and then as the flame kind of stops propagating if the flame is held constant. But then you can imagine if that flame were to chase along the fabric, it's eventually just going to kind of burn it to completion. So sample orientation, is the sample vertical? And you've got, the flame wants to propagate up due to buoyancy. Or is it horizontal? Is there a 45-degree angle? All these things are important to consider when considering, flame spread of your materials as a function of that chemistry. Polymer chemistry, or I should say material chemistry, will dictate heat release. So I mentioned cotton, which is not really a polymer, but is a natural cellulosic material. It's got its own chemical structure. It wants to char, it wants to smolder. That's a function of its chemistry. Polyesters, polypropylene, polyethylene type fabrics don't want to char, although some polyesters do, but for the most part they don't want to, and they melt and flow. So that chemical structure will dictate polymer decomposition products, and those decomposition products will have their own potential heat releases. So polyolefins are going to give off hydrocarbons. Not surprisingly, they're going to give off high levels of heat release. Polyaromatics, Nomex, Kevlar, we're going to give off a mixture of products, including hydrocarbons, carbon monoxide, CO2, and so on. So you have to look at those chemistries. And I could give a whole other seminar on it, but just to kind of demonstrate. So here's some plastics. These are not fabrics, but just I want to show you some of the chemical differences. You can't treat all these fabrics the same. There's ABS, polycarbonate, PVC, and high-impact polystyrene. And so you look at a cone calorimeter, and the heat releases are entirely different from one another. High-impact polystyrene, very high heat release rate material. Not surprisingly, it's an aromatic hydrocarbon. It's not that different from solid diesel fuel, if you want to think about it, and it burns pretty intensely. Polyvinyl chloride, it's got a built-in flame retardant chlorine into every repeat unit of its structure. Not surprisingly, it's going to have a low heat release. And then you pick a engineering plastic like polycarbonate. It has a middle level of heat release, but it chars and takes a long time to ignite. ABS polycarbonate blend has some of the polycarbonate in there, so it's keeping heat release rate low, but the ABS part ignites right away. So look at your polymer chemistry and it'll help understand some of these heat releases. And with that, I'll hand it over to Andrew, let him talk, and then we'll open up for questions at the end.
All right, thank you, Alex. So today I'm going to be picking up, I apologize, the second half of the test, talking about regulatory fire tests for flame retardancy. If anybody attended last month's webinar, we know Dr. Herschler gave a good summary of a lot of these, and so where we wanted to kind of pick up today is actually go through some of these tests and kind of give demonstrations of what they are and what they look like and what they're actually doing. And so there's a great deal of number of regulatory tests or industry tests that are done at the federal level with the CFR, the Consumer Product Safety Commission. There's building and fire codes, such as the International Building Code and Fire Code, and the Life Safety Code, and the Building Construction Code from the NFPA. In the transportation world, there's the FAA, there's Coast Guard, there's FRA, and IMO regulations as well that all require some level of flame retardancy in the materials that are being used within these occupancies or transportation vehicles. And so what are some of the fabrics that could be covered under these? You got awnings, canopies, tents, curtains, drapes, sleeping bags, protective clothing, uniforms, play structures, interior finishes, decorations, anything for transportation, seating, cushions, and then a whole host of others as well. And so why flame retardants? Why are these important? This is a video from UL that I'll get going here, and fast forward a little bit, hopefully. And it's demonstrating an old room, what they're calling a legacy room here on the left, as well as a modern room on the right. Similar setup, similar layout. They start a small fire right there on the couch and are basically just seeing how the growth will continue through its completion of the test. And so small enclosed space with an open door, so you've got plenty of ventilation. And so what this video is going to be showing here, as you can kind of already see, is the fire in the modern room is already picking up and spreading into the drapes and curtains, starting to create a smoke layer that is going to be impacting heat throughout the rest of the room. And we're getting a much greater flame spread and a much bigger fire hazard with that modern room mock-up that they have. And so, why is this happening and why is this important? So there's a great deal, a number of variables with new buildings and modern furnishings. And so there's a great deal of changes as well that from things that were occurring 50 years ago as far as furnishing your homes. And so the design of houses, for one, has changed a great deal. And so most people nowadays prefer a nice open space for their house, not the enclosed, boxed-off spaces that we kind of had in the past. And so that helps with ventilation. It allows the fire to continue to grow and get larger. And secondly, the fuel loads have really changed as well. And so, legacy room on the left, the old buildings, much different building products. A lot of woods, metals, things of that nature. Whereas, plastics and polymers and fabrics have really taken over, taken over kind of the furnishings that we'll find inside of a house currently. So at this point, we're about 3 minutes in. You still have the fire on the left, pretty contained to the sofa and the pillow where it was started. And you've got pretty much entire flash over there on the right side in the modern room. And so pretty stark difference. You can see the fire on the left now is finally starting to get going, but a pretty big difference between the two. And so that's where flame retardants come in, and why a lot of these federal regulations exist is to try to mitigate some of these fuel loads and hazards that we have nowadays. Okay, so what are some of the key tests?
we're not, with the time we have, we won't be able to go through every single one of them today, and so try to highlight some of them and go through a few of them, show some more videos. And so for interior finishes and products, you have NFPA 701. It's good for curtains, drapes, awnings, decorations, motion picture screens, tents, these kinds of things. NFPA 286, 265, ASTM E84 is for interior finishes. You've got CFR 1632 and 1633 for mattresses. You've got NFPA 289 for furniture. And then you've got CFR 1630 and 31 for carpets and rugs. Clothing-wise, like your normal apparel, CFR 1610 and 1615, 1616 for children's sleepwear. So children's sleepwear have additional requirements for their garments to protect them. And then for PPE or uniforms, ASTM D, 6413, ASTM F 1930. It's good for flash firefighter gear, tested to NFPA 1971, 75, and 77. And then as well as ASTM F 1060 and 1939, which are hot surface and radiant heat tests. And so what I'd like to do is just kind of go through some of the key ones that we discussed and give you a kind of a short description on what they are and kind of give you an idea of what we're looking at. So NFPA 701 applies to a lot of industrial fabrics and textiles that are used. And so there's two test methods within this standard. The first test method is a small-scale test. It's meant for textiles with weights less than 21 ounces per square yard. It's tested inside this small little box that you can see. It's about 2 feet by 2 feet. And the specimen is 6 inches by 16 inches long. It's hung vertically. And it's ignited there by about 1.5 inches premixed methane burner. And it's kept there for 45 seconds. And so the test has two ways that you could fail. If any fragments or drips fall off the specimen and continue to burn for more than 2 seconds, then that's a failure. And additionally, afterwards, you weigh the sample and you determine that if the weight loss was greater than 40%, then that's also a fail. So in this case, you would check the mass of the specimen before the test, check it afterwards. If more than 40% of the weight has been consumed, then you've failed. The second test is test method 2, much larger scale, as you can see, than the first test method. This is for fabrics that have a weights greater than 21 ounces per square yard, and it's tested inside a cabinet that's approximately 1 foot by 1 foot by 7 feet high. And you've got specimens that are much greater too, as you can imagine. So 5 inches by 48 inches, so 4 feet high. So you're testing almost a full-scale drape or a curtain in this case. It's ignited at the bottom by a 3/8 inch methane burner, and it's positioned there for 2 minutes. And so this test is, you can see the time and the requirement put on it, 2 minutes compared to 45 seconds for the previous, is a pretty significant exposure. And so if the specimen continues to burn for 2 seconds after the burner is shut off, then it's a failure. In addition, there's char length measurements that are performed afterwards as well. And so if the char length is too great, basically if the fire has burned up the specimen too far, you will fail the test. Additionally, there's also the falling fragments condition as well. If dripping material or fragments fall off the specimen and continue to burn for more than 2 seconds, then you also fail. Another test that's getting more and more common on interior finishes for industrial fabrics is NFPA 286. This is a test that is determining the contribution of interior finish materials to room fire growth. And so the test is performed inside an room enclosure, 8 feet wide, 8 feet high by 12 feet long. There's an open single doorway, as you can see in the video, at the front. A burner is placed in the back corner. for the first 5 minutes, the exposure of the burner is 40 kilowatts, so something akin to a small trash can fire that would be placed in the corner. And then at 5 minutes, the burner is ramped up to 160 kilowatts. And this continues for an additional 10 minutes. So total test time with the burner is 15 minutes in this case. And so what we're looking for here is that the room doesn't move into flashover. And so some of the indicators that the test looks for flashover are the heat release rate. So this test is done underneath a very large hood. And the heat release rate cannot be greater than 1 megawatt. Additionally, there are heat flux sensors placed at the floor. And the floor heat flux sensors cannot be greater than 20 kilowatts per meter squared. There's also thermocouples placed at the ceiling level. And so the upper layer smoke temperature cannot be greater than 600 Celsius or about 1100 Fahrenheit. Flames can exit the doorway, and there's also paper targets placed on the floor. And if those auto-ignite, then that's another indicator of flashover. So, the test you just saw there, that was a blown-in FR fiberglass insulation. And so in that case, after the 15-minute exposure, there was no flashover. And so that material did quite well. Another common test is 16 ZFR 1633. It's a test for mattresses. And this is a test that its main goal is to delay the flashover of a mattress when it is ignited in a typical bedroom fire. So it tests full-size mattresses. They have to be at least twin size, up to king size. And so in this case, you're going to see this mattress is not going to pass this test. It has a pair of T-shaped burners, one placed on top, one placed on the side, and it's representing burning bedclothes that you would anticipate, a fire originating on top of the mattress and burning. So the top burner is kept on for 70 seconds. The side burner is shorter duration, 50 seconds. After that time, you remove the burners and you allow the mattress to continue to burn for a 30-minute test duration. So in this case, this mattress has not performed very well. And so here's a second test of another mattress that performs quite better. And so you'll see again, you've got the T-shaped burner, one on the top, one on the side. These will go again for 70 seconds and 50 seconds. And in order to pass, the mattress set must not exceed a peak heat release rate of 200 kilowatts at any time during the 30-minute test. And the total heat release for the first 10 minutes must not exceed 15 megajoules. So what they're doing there is they're really trying to make sure that the initial ignition the initial ignition of the mattress with the burners does not create a quick flashover scenario. See if we can speed this up a little bit. Okay, so the burners have been on. They've just turned off. You can see there's a little bit of a flamelet there, still kind of at the top burner, hanging out on the surface of the mattress. Come in, they remove the burners out of the way, and basically this mattress just remains in this very smoldering state for the next 30 minutes, and that's a pass. Next test that I want to discuss, CFR 1610. It's for apparel textiles. It is the test that applies essentially to all garments that are sold into commerce in the United States, except for PPE or children's sleepwear. And so this is a small-scale test. It's meant, it's part of the Flammable Fabrics Act, and it's something that if you're going to sell or distribute garments in the United States, you have to demonstrate that you can pass it. So the test is done and classifies your materials in 3 ways, class 1, 2, or 3. For a plain surface material like a t-shirt, that means that your flame spread is greater than 3.5 seconds up the material. A class 3 material for a plain surface would have flame spread less than 3.5 seconds. We'll show some examples of this coming up. For raised surfaces, you get more time for this. Class 1 is a burn time greater than 7 seconds. A class 2 will be a burn time of 4 to 7 seconds. And a class 3 is, for a raised surface fabric, is anything less than 4 seconds. And so in order to pass the Flammability Fabrics Act, you've got to be a class 1 or a class 2. Anything that's a class 3 is not acceptable in the standard. So test is performed in a small test cabinet. You have a 5/8 inch flame. You've got a sample that's inserted 3 inches wide, 6 inches long, and you've got a small flame exposure time of only 1 second. So if you blinked, you might have missed it there. The burner went down, impinged on the specimen for 1 second, comes back up. In this case, the material didn't ignite, and so it passed. So in this test here, after the 1 second, you had ignition, and you can see the flame spread up the sample and just burned up to that stop cord and broke it. And that's the timing device that lets you know how fast it took to actually spread up that specimen surface. So in that case, the specimen was, the burn time was faster than 3.5 seconds, and so that material would not be acceptable by the Flammable Fabrics Act. Okay, moving on to ASTM D6413. Here we're talking about a vertical flammability test. This is a very similar test to what many people call the old NFPA 701 small-scale test. It's used a lot for PPE, uniforms. There are some requirements in firefighter gear that you need to meet and pass this test. And so it's very commonly used for testing flame resistant fabrics. And so the purpose of the test is to determine whether the fabric will continue to burn after the source of ignition is removed. It's looking at a number of things. It's looking at the afterburn time, the afterglow time, and the char length, and we'll show all examples of these. It's a 12-inch specimen. It's mounted vertically. You've got a small methane flame that's placed underneath it. It's there for 12 seconds. This material here is a FR denim. As you see, it did not ignite, didn't really have any flame spread at all. Here's the second specimen. It is a non-FR denim, and you'll see a much different result. So the material has ignited and essentially consumes the entire specimen. Here's a final test. So this is a polymer-based material, and so it's going to act much differently. You can see it kind of melt and move away from the heat source there and go up. So once the test is done, you're going to take a look at the char length. Char length is measured by just that distance that the specimen, or I'm sorry, the flame burns up the specimen. And so you see in this case, you've got a very small char length on the order of 1 inch for that FR denim material. Difficult to even measure the char length there. On the non-FR denim, you've essentially consumed the entire specimen. As you see, she can rip it in half. And then kind of in the middle ground, you've got the char length here for the last material. So different test methods, different test standards are going to require char lengths of less than 4 inches or less than 6 inches, depending on what you have. And so it all kind of depends on which standard is requiring you to run that test. So one of the last ones I wanted to show was ASTM F1930. This is kind of a cool test that is simulating a flash fire. And so on the left here, we've got a Nomex trousers and shirt. You've got 100% cotton in the middle, and then a polycotton blend here on the right. And so the point of this test is to, again, simulate a flash fire scenario. It's done on a full-scale mannequin. The mannequin is instrumented with over 100 heat flux sensors all around its body. The fire exposure is created by 8 propane burners, creating a heat flux of around 84 kilowatts per meter squared, so a significant fire source for 3 seconds. Underneath these garments, the mannequin's also dressed with cotton briefs and a shirt. And after the exposure, the sensors are there to actually measure how much heat transferred through the material and how much of a burn you would anticipate a person getting from this flash fire exposure. Obviously, the ones on the middle and on the right with the cotton and the polycotton probably don't need to go to the data here to determine you've got a fire hazard situation. And then the one on the left just has a little bit of char in a few spots, but for the most part, hung in there pretty well from that exposure. So some different standards will refer to this NFPA or this ASTM F1930 test. For instance, NFPA 2112 requires that for your industrial garments that only 50% of your body would receive a burn after this test. So again, it's not every test that can be done from a regulatory standpoint, but kind of some of the higher key ones there, and give you kind of an example of what tests and what they actually look like when somebody's asking you, hey, have you run this test or have you performed that test? Kind of give you an idea of what they actually look like. And so to sum up everything that Alex talked about before and myself, heat release rate measurements on textiles can give insight on how a material, as a function of its composition, will affect fire performance. Some of the good examples to do heat release measurements: cone calorimeter, the micro combustion calorimeter, and the OSU calorimeter can all be very useful. There's a need to really understand the heat release of a material, its composition, its chemistry, the fire physics. All these things need to be properly understood in order to really perform, to really understand how flame spread will occur in your material. Regulatory tests, they differ a pretty good deal from, heat release rate measurements and kind of research-based testing. And so, the regulatory tests are really there, mostly looking at small-scale tests on fabrics, garments, textiles. They generally are only a pass-fail, and in order to meet those requirements, you many times have to require flame retardants in them in order to meet those tests. But just because you pass a regulatory test, such as CFR 1610, the 45-degree angle test for apparel clothing, doesn't mean that your material is going to perform well in everything. And so that's where doing some additional testing, some analysis, either heat release rate or full scale with a mannequin, can really come into play and really give you a good idea of how your material is going to perform in a full scale fire scenario. And so that's it for us. We're happy to answer any questions you have for myself or Alex. We'll be here for another 10 minutes or so, and so if you got any questions, please, and I think Haskell, take it from here.
Yeah, thanks, Andy, and thank you, Alex, for those presentations. And to the audience, feel free to enter your questions on the GoToWebinar toolbar, and I will direct those to either Alex or Andy or both of them to get responses. Alex, I have the first question for you, and I apologize if this was covered, but I was just wondering, what is the difference between a cone calorimeter and just a calorimeter? Can't you get the same information from a plain old calorimeter? What's the significance of a cone?
Sure, no, I can explain that. You're correct. So it's a calorimeter is a calorimeter. It's a heat release measurement. The difference is in how you measure the heat release. So if you take a sample and you do the classic oxygen bomb calorimeter where you burn it to completion and you're measuring that the water buildup, the temperature and the water buildup, that's one way of measurement. There's differential scanning calorimetry. Cone calorimeter, what it's doing is it's measuring consumption via measuring heat release via oxygen consumption calorimetry. So as the sample is burning, it's consuming oxygen out of the air. So so you're going from 20.95% oxygen down to some lower number. So for every gram of oxygen consumed, 13.1 kilojoules of energy released. And so the cone calorimeter is the sample sitting on it's sample's laying flat. You're radiating heat on top of it, and it's well ventilated, and then so the sample ignites and the heat release, then occurs from the sample burning. But it's a forced combustion scenario, so you don't take away the heat like in all the other samples that Andrew showed, where the flame is provided and then that flame's pulled away and you let the sample burn. In the cone calorimeter, I'm forcing it to combust. I'm running it through its a really rigorous, well-ventilated fire scenario.
So the cone itself actually does that trapping of the heat, helps with that?
It radiates the heat on the sample, and then so as that sample absorbs heat, decomposes, enough gas comes off, there's a spark igniter sitting above the sample, and then it ignites, although a sample could auto-ignite. As those flames get consumed up, they go into the exhaust stack. There's a sampling ring in the exhaust stack that pulls out a gas sample to an oxygen analyzer, and then that measures the oxygen consumed, and then that gets calculated in the heat release.
Okay. I think this next question is. Oh, sorry, Alex. Were you?
No, I'm done. I just wanted to see if that answered your question.
Yeah. I think this next question is for you as well, Alex. Do you have any comments about a heat transmission index, HTI? Do you know have you heard of that or come across that?
Yes. I mean, I'm trying to remember. I want to say it's associated with NFPA 1971, but I could have that mistaken. So heat transmission, when related to a fabric, at least if I'm understanding it correctly, is a function of how much heat, as that sample is burning, igniting, whatever else, is transmitting to the person wearing it or transmitting to the backside of the sample. So I want to say that I may have this mistaken, but again, I think there's some things within the NFPA 1971 test, which is for firefighter gear. One of the things you look at is, hey, is that person's wearing fire protection gear, they're going into a fire to put out the fire, what's that rate at which the heat transmits through the garment that could lead to first, second, third degree burns of the person wearing it. And so I think that measurement, again, I'm not entirely sure how it's measured, but I think it's in that standard. I think you put a thermocouple or some sort of plate on the backside of the sample. You've got a radiant heater on the other side of the sample, and then you're measuring, how fast that heat transmits through the garment and what the rate of temperature rise on the backside of the sample is. So I need to kind of look at the exact standard that it's referring to, but I understand the concept, at least from a fire protection perspective.
Yeah, no, that makes sense, and I think you may be right about which standard you're referring to there. I think there are other standards as well that allow you to measure heat transmission through fabrics that I'm aware of. I'm going to give this question to Andy. Is there a simulator for the E84?
There are a number of tests that have been shown that people have tried to correlate to E84 as far as simulator. I'm assuming the question is saying, rather than have to do a 24-foot length sample like you would need to do in E84, something smaller scale. And so most results, and Alex, chime in afterwards if you like, a lot of correlations have been found that have worked very well with the cone calorimeter. And so there's a great deal of research out there for many different materials, wood, plastics, that have shown, running the cone calorimeter, you get a good data set, heat release rate, time to ignition, smoke production, and then you can take those results and then correlate them up to the E84 test. And so that's the one that has been found to be the best one to correlate with, and from my understanding. So Alex, I don't know if you've done any of that yourself.
I have with not as quite as good success. So for materials that don't drip and flow, for materials that stay in place, cone calorimeter can mimic E84 conditions, and you can do some math and models to correlate, rates of, the time to peak heat release rate and some of the other events to an E84 rate of flame spread. But if your sample deforms or sags or moves around or drips away or does anything, all bets are off, because then the fire physics is starting to dominate the rates of flame spread in the E84 tunnel test. And then so the fire phenomena can get very complex very quickly, and then that can change the correlations that you would try to establish. So I have found for thermoplastics and for materials that deform, the relationship between cone and E84 is not very strong. And so you have to do a lot of additional tests to really understand that and develop that correlation. The other issue is that the smoke measurement in the E84 is not exactly the same way that smoke is measured in the cone. And then E84 is somewhat operator dependent. You've got a person on a chair sliding along the tunnel looking through all that smoke and stuff and estimating where the flame spread is. Whereas the cone calorimeter, it's an actual measurement of the sample burning and everything else. It's somewhat operator independent. So there is some relationship between cone calorimeter and E84, but you need to be very, very careful if your sample undergoes a lot of physical deformations when burning.
Yeah, and one thing that I found too, Alex, is that even if you're not going through the painstaking motions of correlating perfectly, to it, like to an end result with the E84, just having a material, for instance, that can pass E84 and burning it in the cone, and then burning maybe some new research materials, something that they're just working on, and getting an idea of how that material compares to the quote baseline one that passes, can at least give the manufacturer an idea of what they're doing. If they find, wow, we've got a much higher heat release rate with this new material, this might perform not as well in E84. That at least gives them kind of that heads up moving forward.
Yes, I definitely agree with that. That's very much how I sometimes guide my customers the same way when they submit samples. Yes, right. That is a fair assessment.
And what's nice about having both of you guys do this is that Alex is a chemist and Andrew is an engineer, so you're both approaching this from slightly different perspectives. And so this next question, I think, fits better with the chemist, Alex, and the question is, should polyester be washed and or scoured before flame retardant treatment? And also, do solution dyes on polyester affect the flame retardancy?
Okay, so let me answer the first question. I think that really depends upon the chemical flame retardant you're going to use. There are some chemicals out there that may require surface preparation of the fabric so that they adhere better to the polyester, so therefore it becomes launder durable or what have you. And then it's like any coating applied to something else. If the surface chemistry isn't right, it's like when you paint your walls. If you don't prime it properly or wash it properly, the paint doesn't stick properly. So the same thing would be true for certain flame retardant chemicals. If you don't treat the surface of the fabric correctly, the chemical won't adhere, and then it will come back off again, and you lose some of the durability. If you have a reactive flame retardant, on the other hand, you may be required to prep the surface so that you have the right chemical bonds for that reactive flame retardant to bond with the polyester. Going to the subject of color and how that affects flame spread, in general, there is some correlation, classically, which we can think about. White materials reflect heat, and dark materials absorb heat. And I have seen multiple samples where, black samples ignite faster than white samples. So, but, assuming that the color is dominating, I think it's really going to be the color of the fabrics dictating the flame spread rather than the chemical pigment itself. I don't know if a calcium carbonate white pigment would give a different flame spread performance than a titanium oxide pigment would. I would think that the color would dominate, at least from what I'm seeing. So if you're dyeing your fabric particular colors, I would think you're going to see ignition would be slower with a white fabric and faster with a dark fabric.
You're talking about radiant heat ignition.
That's radiant heat ignition. If you're talking about a open flame ignition, on the other hand, I think they're going to ignite roughly at the same. And then maybe you might see some minor differences depending if you're using an organic pigment versus an inorganic pigment. Something
right, but these dyes and pigments tend to be at such low concentrations. Have you done any work where you see differences?
No, not unless that particular treatment process has somehow degraded or changed the fabric or oxidized it in some manner. So I gave the example of bleached surgical cotton. So if you take cotton straight from the seed pod, it's a little bit oily to it, but it's kind of brown. If you remove those surface oils, just wash it, you'll get a brown cotton fabric. If you bleach it, get it to a particular state where it's white, not only have you removed off all the other pigments and everything else, you've actually begun to oxidize the cotton itself. And so its chemical structure has changed and therefore could burn a little bit. And it does burn faster, as I showed with my own results. So if the function of dyeing the fabric is chemically changing the polyester or the nylon or whatever else, and you're chemically degrading it in some way, I could see flammability gets worse as a function of the dyeing process. But otherwise, from an open flame perspective, I wouldn't think so.
Right. Let me ask this next question. I'm not sure if you guys will know this. Is there going to be any change to the CA, I assume that means California, TB 117, due to its incorporation of a cigarette that is not legal? Does that ring a bell with either one of you?
I know exactly what that's about, and that's a very interesting question. So you're right. The cigarette that they use in the TB 117 test is a non-self-extinguishing cigarette. So if you have friends who smoke, ask them about the self-extinguishing cigarettes, and you'll hear quite an earful about it. The way that self-extinguishing cigarettes are supposed to work is they put these little speed bumps on the cigarette, these little bands. And so in theory, if you're not puffing on it constantly, it goes out. So I've actually talked to my friends who do smoke, and they say, yeah, we have to suck down these things faster to keep them lit. Go figure. So what's interesting about this is that those reduced ignition propensity cigarettes that are currently on the market, that's the only ones legally you can buy. And yet in the TB 117 standard, they use a NIST standard cigarette that doesn't have those little bands, so it burns and smolders differently. There's a lot of political issues going on with this California TB 117 standard, that the focus really of that standard appears to be that they feel that cigarette ignition is the primary fire risk for seats, not open flame, and therefore they wanted to change the test to push their particular belief of the standard. This is also going to be somewhat subject to change if Consumer Product Safety Commission decides to change the standard and come up with an open flame standard, because federal standard trumps state standards. So whether or not California will change its rules remains to be seen. People have tried to point out to California that, hey, you're using a cigarette that's technically not legal in commerce. And California has ignored all the current states to change it, a request to change it. But these reduced ignition propensity cigarettes are starting to be shown that, sometimes they don't always work as advertised. So maybe it's not really a fire safety benefit, at which point maybe those cigarettes, that changes, then we go back to the traditional cigarettes without the bands. It's a really complicated mess, and it's not going to get resolved until Consumer Product Safety Commission steps in with an official rule. So this unfortunately means, for those of you on the phone who have to meet the standard, do not expect clarity on the rules anytime soon.
Excellent response. Thanks, Alex. Listen, I want to let everyone know that we're just a couple minutes past 3 o'clock now, and if you need to jump off, of course, do that. We're going to keep going though, so you're welcome to stay on. We still have some questions coming in. Next question has to do with silicones, and the question is, does oxygen consumption work for all materials, for example, silicones?
That's an excellent question. You do, for silicones and materials that have a different rate of, they react a little bit differently in oxygen. So that equation that I gave earlier, 1 gram of oxygen consumed equals 13.1 kilojoules of energy released, does not fully hold for silicon, so you have to put a correction factor into the cone calorimeter. But you can use oxygen consumption calorimetry to measure the heat release rate of silicones. You just have to factor in the right correction factor, which I don't remember what it is off the top of my head, but you can plug that in the raw data for the cone calorimeter measurement and just correct it that way.
Yeah, it makes sense based on chemical structure. Next question I'll address to Andy, but then Alex jump in as well. How do you reduce the variability when you're testing? What's the most reliable and repeatable testing method for flame retardant fabrics? Let's go with the first one first. What do you do in your testing work to reduce the variability when you're?
Yeah, good question. So, I mean, this comes up a lot because, you'll hear a lot from people that, hey, we tested one day at this lab and everything was fine, and then we tested the exact same thing at a different lab 2 months later, 6 months later, 1 year later, and we got a completely different result. And so, one of the things that you need to do, of course, anytime you're running any test is to remove all as much variability as you can. And so, following the procedure, making sure your equipment is calibrated, operating properly, that you're getting the right result. And so, one thing I like to do if I'm running the cone calorimeter or if I'm running one of these vertical flame spread tests that I showed videos of before is I always like to have a baseline material around. So with the cone calorimeter, for instance, they recommend, and we found great consistent results with burning a piece of PMMA every so often. And you should get the same general range of results. And as far as heat release rate, when the peak comes, the time to ignition, your smoke production, all of that stuff. And so if you're running that, if you're keeping your equipment up to speed with its calibrations, and you're doing some baseline tests as well, you should be able to stop any issues that's coming up with hey, why is this result not repeatable? Why are we getting bad why are we getting bad data? Something like that. You can really stop that before it ever happens because you've got everything running the way it should be. And I do the same thing with vertical flame spread tests and things like that. I have a set of baseline material that I like to run before we'll run some tests, and we'll run them, and we'll make sure that we're getting flame spread times, char lengths, things like that that are consistent for that material that I saw a year ago, that I saw 2 years ago, that I saw 5 years ago. And so that's kind of the key to making sure that you're getting good, consistent test data is make sure the equipment's right, calibrated, and that you're doing some baseline testing to keep on top of it.
Alex, you got anything to add to that before we go to the next question?
No, I would second that. That's exactly what you're supposed to be doing, is running as per the standard, keeping your instrument well run. The only thing I would add is for open flame tests, for some standards, there actually are calibrations for the flame itself. UL 94, for example, does have a separate substandard just for calibration of the burner itself. But if you're running internal standards and you're running, you're keeping logs of maintenance and everything else, you should be fine. The only other thing to look at is, especially for some fabrics, depending on their density and whether they can absorb water or not, look at the samples, the conditions under which those samples were conditioned. Is it a high humidity day? Is it a very dry day? Has the samples been conditioned the same? But otherwise, as long as you're doing meticulous methodology, you should eliminate all variability.
Right. Good point, Alex, with the specimen conditioning. And so a lot of the test methods will require either they be put into an oven or they be conditioned at a certain temperature, certain humidity, and then you need to test them within a very certain time frame. You take them out of the conditioner and test it within 2 minutes, something along those lines. So that's something that can certainly be a factor if you're taking your specimen out and leaving it on the counter for 3 hours and then testing it. It can absorb a bunch of moisture back in and then affect your results. So good point.
And then what is the most reliable or repeatable testing method for flame retardant fabrics? Maybe you guys just answered that. Any of them, as long as you do it correctly. Andy, you want to take that first?
And so it's difficult to say over the wide span of all fabrics that could be used. And so the cone calorimeter has always been found to be very repeatable and very reliable. we've had excellent results with the vertical flammability test, correlating, results in a small scale test to a full scale test. And so I wouldn't just pick one, and I usually don't recommend just one when someone's doing a full, hazard analysis and fire hazard. I like to kind of approach it as how's the material going to be used, what makes the most sense test-wise to really look at it and to analyze the fire hazard. And so usually it turns into a combination of a cone calorimeter, a vertical flammability test, and then, if we can, scale it up to, a full burn on a mannequin. Not necessarily the flash fire test where you've got, 100 sensors on it, but just something where you've got it on a non-combustible mannequin, and you can actually visualize how this material is going to perform, if it was ignited in a real-world scenario.
Alex, you want to chime in on that one?
Yeah, I'll give a little bit more nuanced answer. So since each of these tests is looking at flame retardancy in a specific fire risk scenario, ideally, if the test was designed correctly, it should be very reproducible within that test scenario. But you have to realize when it comes to flame retardancy that what's an appropriate flame retardant for a fabric on a curtain and passing that particular test may not be appropriate at all as a flame retardant for, a seat cushion or for, in a subway car, or, a fabric that's going to be used, for somebody who's going into a fire scenario. So each of these individual tests looks at its own individual fire risk scenario. You tailor and optimize the flame retardancy for that fabric in that scenario, and you have to realize just because it worked in one scenario doesn't necessarily mean it's going to work in another one. So you have to look at each of these individual tests, and so sometimes you may need to do more than one test, but if at the end of the day you got to sell in just one test, that's the one you should be looking at, and as long as that test is reproducible with your material in that test, you should be fine. If you're having reproducibility issues, you should look to your, what's changed in your fabric, or you should see if this is a test, that has some known operator issues with it. The person's holding the flame like in UL94 versus the flame's mounted and touching the sample the same way every single time, and that could account for the variability.
Next question. Oh, Andy, you wanted to say something? That kind of takes us to our next question. Are there any best practices that you guys would recommend for preparing fabrics or textile samples for MCC measurements? And Andy, why don't you take that first? MCC measurement. Alex, you want to jump in?
Yeah, Andy, sure. So microcombustion calorimetry, since you're measuring milligrams of material, as long as your sample's uniform, you don't have some unusual weave or structure to it that, would result in a heterogeneity at a milligram scale sample, the sample preparation for it is really dead easy. There's not even a conditioning requirement under the ASTM standard, unless, like I said, for some reason your sample's particularly sensitive to humidity conditions. Otherwise, as long as it's uniform and it's everything's been applied at the same level, you snip off a couple little pieces, you put it in the MCC combustion apparatus, and off you go. It's really very easy. If you ever thought that you had some sample heterogeneity issues at the milligram scale, hey, I wash it and I think my flame retardant coating is coming off, but I can't tell, you can actually pick it up in the MCC test. You can see, hey, I sampled this point on the fabric, I sampled this point on the fabric, and lo and behold, I'm seeing a lot of variability supposedly on the same fabric, then yeah, maybe you've got some issues at the milligram scale. But otherwise, there's not a lot of sample prep required.
Gotcha. Does the shape or size of the sample affect the heat release rate?
In the MCC, no. In the cone calorimeter, yes. The size of the sample, according to the standard, is supposed to be a 4-inch square. So assuming you're testing everything as 4-inch squares, you should see the same thing. But sample thickness and the areal density of the fabric will change the result. So if I had, let's say, for the sake of argument, I've got a thick, terry, cotton type fabric, that's 0.1 inches thick, and then I've got a very sheer fabric which is 0.001 inches thick. They're not, even though they're both made out of cotton, they're going to have different densities, different thicknesses, which will affect heat release results.
Yeah,
that's going to change the rates of burning, change the rates of pyrolysis, and everything else. So ideally, if you want to compare the same formulation, same material side by side, everything should be the same: thickness, areal density, all that. But you could do, hey, I've got two different fabrics I'm selling. What's the heat release? They're different materials and different densities and everything else. Well, then, hey, that thicker fabric may burn worse or may give off more heat release, or the thicker fabric may be more prone to smolder and charring because it has some thermal mass to it versus the very thin fabric, which does not. So, yes, it definitely has an effect.
Yeah, in fact, you had mentioned, I think, raised or fabrics with different kinds of surfaces. And in fact, Andy, I wanted to ask you, you talked about CFR 1610, and there was a special type of that test for fabrics that had raised surfaces. Do they specify what is meant by a raised surface? Is there some, what's the definition according to that CFR 1610 of what constitutes a raised surface?
Yeah, I'd have to look up exactly how they define it, but yeah, there is a series of requirements in there that put you into the plain surface or put you into the raised surface. So, kind of the easiest way to think about it is if you've got a bathrobe or a knit sweater or something like that. That's a nice raised surface.
Yeah, like a fleece fabric, maybe.
Exactly. Yeah. And then anything t-shirt to polo shirt related, that's your plain surface.
Okay. Okay, well, I think that's all the questions we have for now. I want to thank everyone for tuning in again. I want to thank Alex and Andy as well. Up on the slide you're looking at there, you have the contact information for all of us if you'd like to follow up. You will be getting, all of you who are listening, you will be getting a follow-up email from the Industrial Fabrics Association International, and it will give you some instructions about how to download this presentation in different forms. And I'd like you all to please mark your calendars for April 19th when we'll have the next webinar in the series. And this is going to be given by Kelvin Shin, who spent a number of years in the industry. He's now serving as a consultant. The topic there is going to be commercial flame retardants, properties, and applications, where he's going to go over all the variety of different flame retardants that are available commercially, and for what they might be best applied. So thanks again, and we'll talk to you again in 2 months.
Okay. Thank you.